Hello, lovelies. Today we are going to talk more about polynomials. We're going to focus really on these complex roots. So we've talked about polynomials where they actually have the same number of x-intercepts as they do roots. So when you factor it, you have, if it's a degree 5 polynomial, you have 5 actual x-intercepts. But that's not always the case. We can have complex roots, just like if you think about a quadratic. So if you think about your typical quadratic function, we often have 2 real roots. But we know that quadratics can have absolutely no real roots as well, so we get imaginary roots out of them. So what we're going to talk about today is what that looks like when we have a polynomial. So what is a complex root or a complex number? It is in the form of a plus bi. So this allows for those imaginary numbers. A is a real number, and then we add the imaginary unit, the bi. Now, keep in mind, technically the number 7, for example, could be considered a complex number. It's just plus 0 i's. So that's just how the form is. And then same thing over here, this would be like 0 would be your a value plus 6i. So that's also a complex root or a complex number. When these are actually roots, you're going to also have the x involved. So I said complex root, but then I talked about complex numbers. So when we have the root, then it's going to be like x minus 3 plus 2i, right? So these roots get pretty ugly looking, but that's what they are there. Okay, so what is a complex conjugate? Well, if you remember, where do these imaginary numbers come from? They come from our quadratic equation, right? X equals negative b plus or minus the square root. Oh, that's the key right there. Plus or minus the square root. So because whenever we take a square root, when we introduce the square root into the equation, we get 2 potential outputs, a positive or a negative version. So because of that, we end up with these things called complex conjugates, the positive and the negative version, because they always come in pairs. Once again, they always come in pairs. This is super important going forward. They always come in pairs. So for example, if you have a degree, let's say we had a degree 6 polynomial, right? And we wanted to factor that down. We could have 6 real roots. Well, that's great. What if we only had 4 real roots? That's also a possibility because 2 of them could be imaginary, but they always come in pairs. So if we're talking about imaginary or complex roots here, they're coming together. So if you had a degree 6 and you realize, oh, hey, look, I have an imaginary, you have 2 at least, or 4, or 6, or 8, or they come in pairs. They always come in pairs. So what does that mean? Well, if you have 2 plus I, the complex conjugate is 2 minus I. Again, it's all about that plus or minus, which comes from introducing that square root. Same thing here, 3 minus 4i would, oops, this should be a plus. Get it together for now. That one should be plus. So if you have 3 minus 4i, this one better be 3 plus 4i. Correct that in your notes template if I haven't already done it for you. And then also, we can also have, remember, not everything's going to perfectly factor out of our radical. So you can also have a radical left over. So you might have the square root of 5 left over, and then your I came out. So we have 2 plus I root 5 and 2 minus I root 5. Both of those would be complex conjugates. Again, they always come in pairs. You always have a positive and a negative option because of the introduction of, us introducing a square root. Hey guys, today we are going to take those complex roots and prove that when we multiply them together, we end up back with numbers we recognize, which is how we know we go from a quadratic equation to imaginary roots, and then we're going to go back to something that looks like just like a normal quadratic equation. So we're going to start by multiplying these 2 things together. So you're going to need an area model because we're multiplying 2 binomials together. So we're going to take our negative 4 plus I and our negative 4 minus I. And again, keeping in mind that these are complex conjugates, which means they came out of something like the quadratic formula. So when we multiply them back together, we should end up with something that looks familiar to us with no i's left over. Negative 4 times negative 4 is 16, negative 4i, positive 4i, and negative I squared. Okay, well look, these middle terms cancel out, which is what I expected. I don't want any i's left over. And what do we know about I squared? Well, I squared just equals -1. So here I can replace this I squared with just a -1. So what I end up with is -1 times -1. So this is just 1 in this box. And then we add our like terms, which is going to be 16 and 1, and we end up with just a whole number 17. So again, that's kind of what we expect from something like this because we're multiplying these I terms, these complex conjugates together, which is what gets us to something normal looking. Same thing's going to happen here. This time we also have radicals to contend with, but it's all going to cancel out anyway, so it's okay. I root 3, 1 minus I root 3. 1 times 1 is 1. I root 3, negative I root 3, check that out, that's what we expect. And then negative I times I is negative I squared. And then the square root of 3 times the square root of 3 is just 3. So we end up with 3 times negative I squared. And again, I squared is just -1, so this piece right here is going to become +1 again. 1 times 3 is 3. We combine our like terms and we get plain old 4. How cool is that? Okay, so what's the complex conjugate of A plus BI? Again, that's the standard form or the expected form for a complex number. So what would the conjugate be? That would be A minus BI. Again, when you multiply those together, the I terms are going to cancel out. So what's going to change here? Well, we're just going to subtract the 2I. So this will be 3 minus 2I. Okay, what happens when you multiply a complex number by its conjugate? The i's go away. Okay, so you end up back with a real number. So the imaginary numbers go away. They cancel out. Okay, so for each number pair before, we're going to write the factored form given the roots. We're going to write it in factored form. We're going to write it in standard form by multiplying it out. Okay, so just a quick reminder here. If you have a fraction, remember this is what x equals. So you would have to multiply by 4 to move the 4 over to the other side, and you get 4x, and then you get 4x equals 3. So then you'd subtract 3, again, inverse of zero product property, so we end up with 4x minus 3. This one's just going to give us x plus 5, moving it to the other side, again, reverse of zero product property. So my factors are x plus 5 times 4x minus 3. Okay, to convert this, we're going to have to multiply these things. Well, this should be very familiar at this point, and you should be able to convert that to standard form, which will give you 4x squared plus 17x, combining those diagonal terms. 17x comes from these two boxes, and then minus 15. Okay, same thing when you have these i's here. It's just a little bit longer looking. So what you get is x equals 2 plus I and x equals 2 minus I. So when we bring those back, reverse of zero product property, we get x minus 2 minus I, that's one of our terms, and then x minus 2 plus I, that's our second term. So in factored form, it's x minus 2 minus I and x minus 2 plus I. So when I go to multiply these, I have three terms that I have to multiply. Minus 2 minus I and x minus 2 plus I. Again, complex conjugates, so our I terms should cancel out. X squared, negative 2x, negative ix. Okay, so I'm looking for a positive ix somewhere in here because those I terms should cancel out. Just to check your math as you go. Silly mistakes easy when you have a big area model like this. And then this gives me a positive 2i. So now I'm also looking for a negative 2i to cancel that out. Oh, here's my positive xi or ix. Remember, or doesn't matter with multiplication. So these two terms here will cancel each other out. Again, exactly what I'm expecting to see based on what I know about these complex conjugates. Negative 2i. Oh goody, those two are going to cancel out. Again, what I expect. And then negative I squared, remembering that I squared is just -1. So that also cancels out, leaving me with just a positive 1 down in that bottom box. Now we're going to combine our like terms. So our like terms, we just have x squared by itself. So that comes right down. And then we have negative 2x and negative 2x for a total of negative 4x when I'm adding those like terms. And then our last like terms are right here. 4 plus 1 gives me 5. So that is my standard form. And if you were to use the quadratic equation on that, you should get this as your factors. So that's how that's working there. Okay, so you are going to do the next several examples and make sure you understand what you're doing, and I will post the answer key for you. Okay, so let's talk about why this all matters. Well, we talked last week about factoring these things out, so we're gonna take a look at what these polynomials look like when we have imaginary roots and kind of start describing them a little bit better. So what's the degree of this polynomial? Well, the highest exponent value is 4. The number in front of that x to the 4 term there is 1, so my leading coefficient is 1. This is an even degree polynomial, and it has a positive leading coefficient, so I know both arms are up. Now this is degree 4, so it should have more hills and valleys than that, something more like this, but both arms are going to be facing up. So as x goes to negative infinity, so it would be going this way, what's y doing? Going to positive infinity. And then going this way, as x goes to infinity, what's y doing? Y is still going to infinity. So the end behavior is the same because it's an even degree polynomial. Leading coefficient is positive, so arms up. So my best guess of the graph, given that I only have 2 real roots, one at x equals -2 and one at x equals +2, so I know I have to pass through those. But then I have the imaginary part, so one hill and valley portion is not going to cross, right? Like right here, these could be my 2 complex conjugates. Again, I'm just guessing. I have no idea what this thing actually looks like. I'm just giving an estimate based on the fact that I know I have 2 real roots and 2 imaginary roots. Okay, so now we're going to divide just like we did last week. First, we're going to divide by x equals -2. Okay, and then we're going to use synthetic division here. We're going to take our 1 from in front of x to the 4th. Then I need a 0 for x to the 3rd, a 0 for x squared, a 0 for x, and then I finally get to my -16. Again, we should get 0 as a remainder here because I know this is an actual root. So if you don't get a 0, something went wrong. Bring down your 1, multiply, -2, -2. Again, we're adding up and down and multiplying across diagonally. -2 times -2 is +4, add 4. Times -2, -8, add -8. Times -2, +16, 0 remainder, exactly what I expected. Okay, so now this is my new broken down term. So that's what we're going to use when we divide the second one. Because what we just did was break our degree 4 down into degree 3. This is x cubed minus 2x squared plus 4x minus 8. So now I can use that. I'm going to divide by x equals 2. That comes from this factor, x minus 2. And I'm going to use this new degree 3 polynomial. So this is going to be 1, -2, 4, -8. 1, multiply, 2, 0, multiply, 4, multiply, 8. Look at that, exactly what we expected. So now we're down to a square term. This is x squared plus 0x plus 4. Okay, x squared plus 4, we need to now factor using the quadratic formula. Or in this case, this just equals 0, right? So we could subtract 4 on both sides and we get x squared equals -4. Take the square root, take the square root. X equals plus or minus I, because I pull that I out, and then the square root of 4 is 2. So it's actually plus or minus 2i. Would be your x values there. You could use the quadratic equation and get the same thing, but in this case, it's way easier just to do it this way. Okay, so now we get our original factors were x plus 2 and x minus 2, x plus 2, and x minus 2. So those are my first 2 factors. And then I get x equals plus or minus this. So when I bring them back, it's x plus 2i and x minus 2i are my other 2 factors. Again, 2 real roots, 2 complex roots or imaginary roots. Okay, when you graph this in Desmos, this is what it actually looks like. So notice our imaginary roots are coming from this section down here because this is a degree 4 polynomial, but it kind of looks like a quadratic with this weird flat section here, right? Okay, this point down here is -16. So increasing, where's this thing increasing? Well, let's look at it. It's increasing from that point down there all all the way this side, right? So the increasing portion is going to be from that negative 16. So from negative 16 all the way to infinity. Now at 16, it's not actually increasing or decreasing, it's just sitting still. There is no change. That has a slope of 0 right there. So it's not including the negative 16. And of course, infinity is not an actual location, so it doesn't include infinity either. It just approaches infinity. Okay, where's this thing decreasing then? Well, if it's increasing on the right-hand side, then it must be decreasing on the left-hand side right here. So as we go from negative infinity to, so we're going from negative infinity now over here, right? Negative infinity as we go toward that negative 16 point. Again, not including those values because that point right there is just a sit still point. Okay. So what if you have a bunch of hills and valleys and you need to do interval notation? Same idea. We're just going to focus on, let's start with decreasing because we did that in this color last time. So decreasing from here to there, right? Those values, as we read left to right, the y values are falling. Also decreasing from here to here, right? So let's talk about those decreasing intervals. Well, we have from negative infinity, oops, that's not an infinity, that's going to be an 8. From negative infinity to this point right here, which is negative 2, we are decreasing. And then we are also decreasing. We use this U, this uppercase U looking symbol, which means a union. It's also decreasing from 0 right here down to here, which is an x value of 2. Again, those points aren't included because they're sitting still there. The slope is 0 there. All right, let's talk about increasing then. So for increasing, we're increasing here and here. We have 2 different increasing intervals. So we're going to say from those values. From negative 2, again, not included because we're sitting still there, to 0, we're increasing. And this is a union. We are also increasing from positive 2 to positive infinity. Again, remember for interval notation, you're going to use brackets if you're including the point and parentheses if you are not including the point. So that's how that works. You try those next examples and let us know if you need help. Come see us in office hours. All right, so on this you try, hopefully you're giving this your best attempt. I have already done it, so I'm just going to walk you through it. If I can get this screen where I need it. Here we go. Okay. All right. So when you look at this, we have a degree 4 polynomial. So we're going to write out degree 4. Our leading coefficient here is going to be positive 1. So I know that means that my arms will both be up because I have an even degree polynomial and a positive leading coefficient. So that means both arms will face up, same end behavior. So on the left, or as x goes to negative infinity, y goes to infinity. And on the right, as x goes to infinity, y also goes to infinity. My best guess of what this graph is going to look like would be something like this. Again, I know that I have actual roots, one at positive 3, one at negative 2, because they told me that up here. So I know those are real intercepts. And then I don't know what this part looks like. So I'll be honest, I have no idea what this section in here is going to actually look like. I just know it's got some kind of turning happening that doesn't cross the x-axis. Okay, keep in mind, polynomials can start to look really, really funky, and it's not very obvious where these hills and valleys are always. So just keep that in mind. Again, this is a rough sketch just based on the fact that I know I have 2 actual intercepts and then a degree 4 polynomial, meaning that I must have 2, again, remember they always come in pairs, I must have 2 complex roots. So we're looking for the 2 complex roots because they're not real numbers, right? They don't actually cross the x-axis. Okay, so we first need to divide by the first root, which was x plus 2. So negative 2 is the actual intercept there. So I'm going to use synthetic division, list out all my coefficients, and then do the process of synthetic division. Again, you better get a 0 over here. If you don't, then something went wrong and you need to try again because we were told these are roots. So if you don't get a 0, you did something wrong. Check it again. Okay, so when I do that, I get this now degree 3 polynomial. Great, moving in the right direction. I'm going to take those coefficients, so 1, -1, 4, and -30, And I'm going to divide by my second root, which is x equals 3. So then when I do that, I get down to a degree 2 polynomial, or quadratic as the case may be. And now we can use the quadratic equation to factor these. Keep in mind, when you're looking for complex roots, that is the only way that you know how to find them other than completing the square. So you could complete the square to do this, or you can use the quadratic equation. Either way would be fine. Kind of personal preference. I did the quadratic formula here. So I plugged in x equals negative b, so negative 2, plus or minus the square root of b squared, 2 squared, minus 4 times the a value, which is 1, times the c value, which is 10. Notice you're going to get an imaginary value in there. If you didn't, again, we're looking for complex roots. So if you don't get an imaginary one, then probably something went a little off here. Or you could have a radical left over that's not a rational root, okay? All right, so when we do this and we simplify all the way down over here, we end up with negative 2 plus or minus 6i all over 2. That can be simplified further because both negative 2 and 6i can be divided by 2. Remember, you can only divide by the denominator if all the terms on top are divisible. So they are in this case, and this gives us 2 different roots. Again, complex conjugates, they always come in pairs. So we end up with x equals negative 1 when we divide 2 by 2, negative 2 by 2, plus 3i, or we get x equals negative 1 minus 3i. Either way. Okay, keep in mind, that is what x actually equals. So we have to do inverse of zero product property to find the factor. So that's the root. We want to go back to factored form. So what we're doing here is if x equals negative 1 plus 3i, well, I need to move the 1 over, so I add it, plus 1. So now I have x plus 1 equals 3i, and then I need to subtract 3i, subtract 3i, and we get x plus 1 minus 3i. Again, that's how you actually find your factor when you're given a root. And it looks ugly. It's definitely not a beautiful thing here, but it is your factor. And based on that multiplication that happens above, right, they're all going to cancel out and get you back to something with only real numbers in it. Okay, the magic of math, right? Okay, last but not least, go ahead and check out what it actually looks like in Desmos. So when you graph this in Desmos, you'll notice it kind of looks like a parabola that kind of got twisted a little bit. My drawing's not perfect. It's a rough sketch, of course. But it just kind of curves down. That's how you know it's not a parabola. But also, it's not very obvious that it's a degree 4 just to, unless you've done a lot of work with this. I did note my minimum value here because that's going to be important for determining where I'm increasing and decreasing. So again, I just clicked on that point and Desmos told me what the point was. So from negative infinity to that minimum point there, 1.387, we are decreasing. As I read from left to right, my y values are falling. Once I hit that minimum though, now my y values are increasing as I read from left to right. So I'm increasing from that point 1.387. Again, we're not including that point because it's sitting still at the minimum. It's not increasing or decreasing. And then we go to infinity. Hopefully that makes sense. Have a wonderful rest of your day.